Today, I wanted to talk about, in keeping with our theme of doing design stuff on Friday, an overview of some software patterns. One of the things that makes experienced developers more productive is not so much the fact that they're actually better programmers or better coders, but just that they've seen everything lots of times, and after failing to solve it correctly the first 3 times, they eventually build up this library of, when you see this problem, use this solution. When you see this problem, use this solution. And there is kind of a movement to codify this knowledge in with many books called design patterns. And I think some of that idea is good in that it does give you kind of ideas of how to address certain problems. And on the other hand, you can take it too far and try and get carried away with it and come up with some grand language for, higher level programming language. The seminal work on that is by the Gang of Four, who I mentioned in the notes, and it's called Design Patterns. That book is worth a look through. There's a number of other things called software design patterns and the like works out there. Some of the things I'll talk about today are in that book, but I'm really going to cover a wider range of scale in terms of kind of design patterns and architectural patterns than is covered in that book. So this is just an overview. And I wanted to start with data structures. Data structures are the programmer's friend because they let you think at a higher level than you would thinking about in terms of the elementary basic data types, arrays or integers or whatever. And there's some data structures that are useful over and over and over again. Now, you'll talk about data structures in the algorithms course a lot, but algorithms courses, when they talk about data structures, are interested in how to implement this data structure with this interface efficiently. Okay. What we're interested today in is just what these interfaces are. That if you have something that needs kind of this interface, there's a well-known structure that has that interface, and go and find it in a library, or if you can't find it in the library, build the generic version and then use it. Okay. So one example I'll start with is there's a whole class of things called dictionaries, or that have dictionary semantics. All right. These are container data structures that you can store objects based on a keyword and then retrieve them back based on a keyword. Okay. And so the basic interface is like insert key. I won't give the types, but think of all my types here as objects. And there's an R in there somewhere, insert. And then lookup key, which returns you the object that you stored, and then maybe remove key. There's lots of different things under the hood that implement this. Hash tables are a common implementation of this. There's something called A-lists, or association lists, that you see in Lisp and Scheme that also implement dictionary semantics. And so if you decide this is a good data structure, these are the routines that you want, go look for something that satisfies it, like a hash table or whatever. If you don't have any of these supplied in a library, just go and build something that does these things and make it a generic dictionary thing, and then incorporate it into your program. And you'll find you might be able to reuse it in a number of places. It lets you, once you know how to build one of these things, they're easy to build, and then you can use them. So it saves you from having to think custom every time. One thing about if you find yourself having to build data structures yourself that you don't have a predefined library, don't over-engineer them in the first pass. Whenever I have to build these things, I don't go and build a hash table. I don't go and start out and build a complicated data structure. There's also, let's see, heaps are another data structure that do this for you. What I do is I just build a simple linear search list and I go search it. It's inefficient as all get out, but it's fast to program, it works, and it lets you get on with the rest of the task. So that's a moral. Don't over-engineer your components on the first pass. Arrays are basically things that satisfy dictionary semantics where the keys are integers. You've seen them useful. Sometimes it's useful to build the Java vector version that's self-sizing and build that as a data structure if you don't already have one. Let's see. Hopefully you've all seen the stack data structure before in either the Scheme course or other places. It has 3 basic operations. Okay. Push, you push something on the stack. Pop, oops. And sometimes you get something called TOS for top of stack. Okay, stacks follow LIFO semantics, which is they're containers that have last in, first out. So you do a set of push operations, which is analogous to an insert. They put things into the container. Then you do pop operations, which take things out, and they come out in the reverse order that you put them in. So the last thing you put in is the thing that you take off. These are very useful for things related to, as you know, subroutine calling, implementing recursion, implementing parameter passing. Most of the time you don't have to worry about that because you can use the programming language stack. You can declare local variables, call methods, get return values, and behind the scenes the programming language is pushing stack frames on the stack with your variables in them and then popping them off as you return. Sometimes you'll find that you need to do some recursive algorithm like a tree walk or something, but you won't be able to do recursive procedure calls because you're doing it in some background scheme, or it has to proceed in some event handler that only gets to run a few steps and then has to return. And then you have to implement the whole stack protocol by hand. So if that happens, don't freak out. There's nothing magic about that protocol. You just implement a stack data structure. You push your arguments on, you push any state that you need to decide what you're going to do next. Then you do the next step, and when you need to return, you just pop your previous state off the stack. Okay? It's important to be able to reproduce all of the programming technology that the language gives you from scratch, because in many circumstances you'll have to. Sets, semantics. These are very good and useful under certain circumstances. Yeah? Somebody say something? No. Standard set operations, union, set 1, set 2, gives you a new set. Intersection. Yikes. Member returns a Boolean if, I'm sorry, this should be set, comma, element. All right, I'm writing these in kind of a procedural form rather than a method form. But this says if this element is in this set, then return true, otherwise not. Very useful to know sometimes. Sometimes you'll get combinations of these, like you can sometimes get something that looks like an array or a dictionary that also has a member function on it. So you can, give it some value and say, is this value in there at all? Union, it's nice to have 2 flavors, one of which takes the 2 sets and just does a straight union on them. Another one does a unique union on them so that it removes any duplicate members where you have to define duplicate in some way. But there's a lot of algorithms or situations where you find yourself manipulating arrays and stuff by hand, and then you say, aha, what I'm really doing is set operations, so I should go define myself a set object, and then my life will be easier, and it will be. Let's see. Final one that's useful more for representation are trees. Trees you see all over the place. Presumably, you know the tree data structure. It's a bunch of circles connected by lines. A lot of our data structures look like circles connected by lines. This has the property that any node can have 0 or more children, and the children are the things that the arrows out point to. But each node can only have one parent. That means there's only one arrow going into each node. And so it's a unique parent. So from any leaf node, you can always find a unique path up to the root. Okay, trees are wonderful for representing, even if you don't expand them all out, for thinking about searches, especially game searches or pretty much any sort of search operation is a natural for trees. You saw the kind of what was it? The algorithm in the game to try and figure out the connected subset is nicely formatted as kind of a tree walk around this the connected set. Trees are a good application for stacks, since you can do a depth-first tree walk nicely implemented with a stack by storing kind of the current set of nodes, pushing the current set of nodes you're working on the stack, doing the child nodes, and then when you're ready, pop this node off and work your way back up. Tree search is a perfect thing for stacks because the walk of depth-first traversal of a tree follows perfect stack semantics. Gobs of trees are just nice, useful representations for data. Not too much more to say about them. Okay, here is the book. The notes will give you some of the interface methods. I probably shouldn't write them out. Here's one of my favorites. It's not so much fun to implement, but it has a lot of uses. The FIFO queue. All right, I like to draw them like this. This is, we've seen this, an instantiation is when we were talking about event queues. These have insert and remove operations, just like our stack. But the semantics are slightly different. The order in which the objects come out are exactly the order in which they went in. The data structure remembers the order in which you stuck in the things, and then when you do removes on this thing, it pulls them out in exactly the same order. This is very useful for things like event queues. It's useful for queuing, say, packets in network architectures. And it's useful for packing just any kind of data when you have stream processing. If you have a stream in and a stream out, and some processes that deal with streams, very useful to be able to have a FIFO buffer to kind of mediate between this guy and this guy, two processes. There is an implementation of this a common implementation, I don't know whether you'll do this in algorithms, called circular buffers, where you use an array to implement a FIFO queue. And the idea is you have a fixed size array, and you have a in pointer, which is where you start writing. It's the beginning of the empty segment, empty part. And you have an out pointer, which is where you read stuff out. And all this up here is filled, and all this back here is filled. So to remove something, you take the next thing off, you increment the out pointer, and you return this value. To put something in, you put it in this blank space, and you increment the in pointer. And when the out pointer, when either pointer gets to the end of the array, you have it wrap around to the beginning of the array, and it's all good. The one thing that you can see running into trouble is if you do lots of ins without doing outs. Eventually, you're going to run these two pointers into each other, and you have to detect that case and tell the guy who's putting stuff in, no, we can't take any more. Okay, so eventually, this thing will only hold a finite amount of information, but so eventually, if no one's taking stuff out, you have to tell the guy that's putting them in to stop, and that process has to block. But if you have two processes that run on average at the same rate, but in short amount of time at different rates, this is very good for kind of mediating the amount of data between them. Circular buffers are your friend. If you can find a library routine that implements FIFOs, by all means use it. FIFO-Q. Another implementation of FIFO that's common is doubly linked lists. You have the, you have a linked list. You have a head and a tail, and then a series of links. And you have links going both ways. So that makes it very easy to take stuff off this end and add stuff off this end. So these things kind of shift around as you do. That's another implementation. But when you're using it, you first want to think in terms of a FIFO queue and then worry about, or hopefully have somebody else worry about, the underlying implementation. Let's see. Another interesting queue structure is our friend from problem set 1, priority queue. It has the same queue semantics, insert and remove, but in this case, the things go in any order, and they come out in sorted order. Okay, so there are a number of data structures that implement that. One is called, underlyingly, they implement that. One is called a heap. Also, you can use red-black trees, binary trees. There's a lot of different things you can do to implement that. But the thing you want to keep in mind as a user is just the semantics. These are very useful, for example, for scheduling. If you have a bunch of tasks and they appear randomly, but when you schedule them, you always want to schedule the highest priority one. You want to go to your queue and always get the highest priority thing off of it. Another way to implement it is just, when you do the remove, scan down this list and, do a max operation and find the best one you can sort on removal. Let's see, last data structure I want to talk about is graphs. I don't have much to say about them except to draw the terminology. Graphs are, again, circles connected by lines. The lines are called edges, and the circles are called nodes. And these are useful. First of all, there's a lot of algorithms and a lot of theory behind graphs. So if you can map your problem onto a graph problem, you then can bring all this theory to bear, and you can solve many. There are many hard problems that, when you think about them in terms of graphs, have easy solutions. And you'll talk about that in algorithms quite a bit. They're a natural map for any used for any kind of traversal or circuit sort of problems. For example, you could think of these as cities and these as transportation links, either interstates or rail links between them. And then you can ask questions like, how long does it take to get from here to here? Can I get from here to here? What's the least number of hops? All those sorts of interesting questions map naturally onto a graph data structure. There's a variant of this, which is circles connected by arrows, called a directed graph or digraph. And this is essentially a bunch of cities connected by one-way streets. So the question of whether you can find a way to get from point A to point B in a digraph is different than a regular graph, but related. That's all I have to say about graphs. You'll get graphs probably a lot more in algorithms. There's some really nice things you can do with graphs that solve problems that you wouldn't think have anything to do with graphs. Graphs aren't really a container, no. They're a representation for certain types of problems. So, as I say, you'll see a lot more of that. I want to talk a little bit about creation patterns. This is when you want to make objects. Right now, we've mainly been using new to create things and calling the constructor. If you have new in your language, that's a useful thing. Otherwise, if you have a language like C, you don't have new, so you have to build it yourself. Often it's good to make things called factories, okay? Factory is a design pattern. A factory is basically a class whose sole job is to make objects of, or instances of a type of object. It could be the objects of the same name as the factory, or could be, one factory can make a variety of types of objects. It's often useful to do things in a factory style and have, say, a create X method than it is to just use the constructor. There's sometimes you have to glue together a bunch of data structures to make the thing you want, or link the thing you're making into a larger structure, and all that's inconvenient to do in a constructor. So factories are nice. Also, if you are trying to share data structures, okay? So you wouldn't necessarily, new makes a new one every time, but say, you wanted a constructor that had the property that if you already had one of these things around, that looked the same, you wanted to share it, okay? Factories can do all sorts of data optimization. They can manage reference counts and allocation, all sorts of good stuff. We saw examples of factory methods in the Java box class. Instead of calling new to make a new box, this is one of the widget containers analogous to JPanel. But instead of saying new box, we would always call these static methods like create horizontal box, or create, what did we call them, struts. Okay, this had a whole set of these factory methods. So instead of using new and then setting up the layout manager on each one of these, we had utility factory methods which built them all for you. Much easier design. A related pattern is called builder. If you are making if the structures you want to build are fairly complicated and they have lots of hazard relationships, lots of containment relationships, it's nice sometimes to have a builder class whose sole job is to have methods that compose various types of objects into larger structures. Okay, so they let you get kind of elementary structures from a factory and then build them up. For example, to give a weird example, if you're thinking of, you really want something that's a chair, and you allocate, legs and, a back and a seat and all this, you would have builder methods that would compose all these things and eventually be able to come up with a chair, or ideally you'd have a whole language of builder methods that, given some basic components, you could create, arbitrary furniture pieces. So this encourages you to first build an arbitrary language for gluing things together, and then use it to build the specific things you want. It's very useful, for example, when you're trying to reproduce a data structure based on a format you've written out. Okay, say you've done something like a graphics program where you've drawn all sorts of pictures like Visio. You then dump that in some text format which describes all of the line drawings that you've made. You now have to somehow read this text format and reproduce the in-course structure that describes the picture that you've drawn, with a line segment here and a rectangle here and this connected to that. It's much easier to come up with, first something that instantiates the basic pieces and then a language for gluing them all together at various levels than it is to try and do it in any ad hoc method. Okay, so just a concept to think about. The design pattern book has a lot more about builder patterns.
Are things like the way the I/O libraries work, would that be considered that, the way they build on each other? Or is that...
That would be, I think, an example of that. Yeah, they're mostly serial building, but so another class is I think I call interface patterns. These are often useful. Let's start with one we saw yesterday, which was proxy. A proxy is an object that stands in for another object. Okay. Why don't you use the original object? Well, sometimes, as we saw, you can't because it's on another machine. So a proxy has the same interface as the object it's standing in for and handles the same methods. On the other hand, it doesn't usually implement the methods itself. What it usually does is forward those calls to some other structure which eventually does the right thing, and then the proxy translates the results back. Proxies are good for translating across, as we saw, processes or machines. Also good for translating between different types of, well, a little bit about for translating between languages, though there's probably another class that's similar called adapter, which you might think of. An adapter is similar to a proxy, but it performs less of a stand-in function and more of a translation function. It's just trying to translate methods in to of the methods of one interface to the methods of a different interface. So say you have an implementation that you inherited from somebody else of some data structure that isn't quite what you want it to be, but you could wrap it in one of these things that makes it look like the way you want to use it. Or if you have two pieces of code written at different times by different people that use the same semantics but different names, you can just write adapter classes to kind of glue them together. These are kind of glue classes. And as I said, you can use things like this to often call functions written in one language from a different language. For example, you can call native functions written in C or binary functions by putting a Java wrapper around them. And you can spend a lot of time doing this, putting wrappers of one language around things implemented in another language. You can do C adapters on C++ classes and method calls, or vice versa. So, when you think about gluing things together, think about, what I really need here is a proxy. And you wouldn't do anything different than you would do just doing it by hand, but you would tend to, thinking of that way, you tend to do it the same way all the time, which is just much better for debugging and makes things go together faster. All right. Though they are of significant difficulty, and so I can't say much about them except that they exist. For structuring various processes, one is finite state machines, FSMs. I don't know how much you have seen FSMs before in previous, yes? So these are beautiful things, which again look like circles connected by arrows. And computer science is just circles connected by arrows. And the circles represent the state of the system, and the transitions occur on some event happening, or data appearing, or method call. These are very nice in that they let you discretely capture the state of a process, a simple process, so you don't have to store it on your call stack, and so you can handle it in event type control structures or any web type control structures, anything where you have to store your state explicitly because your stack is going to get blown away. There's a whole pile of theory associated with these things, which I highly recommend you read. There's optimization algorithms. There's a lot of variants on them. There's things called finite state transducers that are a variant on finite state machines, which also will kick out a string on transition, and so you can build translators out of those. There are ways to do. There are very good pattern matching algorithms to run on these, but they're mostly useful in programming in Structuring control, very good for any communication protocol that you're doing, often has a state graph associated with it. So you can implement the state graph. Yeah, communication protocols or hardware control, anything of that sort, often has a state graph associated with it where you're in some state and you're waiting for some type of packet or message from somebody else. When you get that message, you either go here or here, depending on the message you get, and so on. Very nice control structure. The second one is you've seen a lot in your first course, is the interpreter. Okay? A lot of times what you're doing, it turns out that you're doing when you're building a program, is making an interpreter for some language that defines what this program is doing. Okay? So you end up actually having to build your own interpreter as part of this program. And so all of the things you learned in 6001 should come in handy. I encourage you to remember a bunch of principles because it's really easy to when you have to do it yourself, forget all the stuff you learned when talking about real programming languages. In particular, remember all of the stuff about environment, variable binding, okay? How to do variable resolution, whether you want to do a stack evaluator or a tree evaluator, or how do you want to store this environment? How do you want to pass it around? How in a given time, when you need to look up a variable, how do you do that? These are pretty easy to implement by hand. A hash table is a pretty good start. You can just, if you just want a static environment, you can just use a hash table and put the values associated with all the variables in them and then pass that around to all of your little processes that need them that can get their values out. But just remember structured variable binding. It's just amazing how few people do. The other thing is, what will we call it? We'll call it stack discipline. Just the notion of doing procedure calls, how to do a procedure call. Push your arguments on the stack, push your return pointer on the stack, jump to the new code, put the return value on the stack, then pop your then pop your old control values off the stack. I'm not sure I spelled discipline right. That's right, stack disciples. But I just want to encourage you to keep these principles in mind should you ever find yourself building a program that's starting to look more and more like you're implementing some language. And a surprising number of things will look that way. Two things that are related to these two, okay? These two correspond to some formal models of languages and are useful for string processing. String processing is something that you end up doing a lot of sometimes, and it is one of the least pleasant things to do in any language except Perl. Did you have a question?
Could you just say, why would a stack discipline not be available in your finite state machine?
Remember, I'm just thinking, when, this gets confusing, but when you're implementing an interpreter for some language, okay, you have to keep two things straight. One is the stack of the language that you're programming in, and the other is the call stack of the language that you're interpreting. Okay, and since you're programming the interpreter in one language, you can't really use it to implement the call stack of the language you're interpreting, usually.
Okay.
So you end up having to build that guy's interpreter that guy's stack by hand, because it might have a different call semantics or variable binding semantics.
Okay.
So
that's probably another point
So this probably gets into the metacircular evaluator issues from Scheme of writing interpreters and interpreters.
Okay. I think I had another question too. When you were talking about the finite state,
yes.
You said sometimes the stack's not available, and so you would.
Oh, there, yes. In a lot of network protocol situations or hardware interface situations, you are implementing the protocol in such a way that you're not allowed to use, allocate a separate thread to just stick around all the time, okay? So you basically have to call into the thing that says, do a transition, and then immediately return. And then if you have not remembered all of the data you need, the next time you call in, you'll forget where you were. Okay? So if you're in an event-based program, for example, every time you return from that event handler, your whole call stack kind of goes away. You don't have any memory of the last time you were there unless you've explicitly stored it in some instance variable that has your state. So, what was I going to say? Oh, yes, string processing. Two useful things are regular expressions. Have you guys seen regular expression languages and the like? Regular expressions are a formal class of languages that coincidentally are recognizable by finite state machines. And they are essentially complex extensions of the kind of star matching function that you get in Java. The basic idea is you can define some kind of canonical pattern, say I want something that starts with CL, then maybe a 3 or a 4, maybe one or more examples of 3 or 4, okay? And say I want to match all things that look like this. You can define patterns in this form, regular expressions, that look very difficult to read until you're used to it. And what this will map to is any language that has CL3, 4, 3, 3. So it has a C and an L and then at least one 3 or 4 followed by any other numbers of C or 3 or 4s. Now, regular expression packages give you the ability to match, to take a string and say, does it match this pattern, yes or no? It also gives you the ability in general to bind variables to various subparts of the string. Like you could bind a variable to this part and bind a variable to this part. So when you process the string, the CL would end up in one variable, and this stuff would end up in the second variable. These are very handy for parsing text files, for doing, converting data from one format to another, for parsing dates, for parsing addresses, email addresses, URLs. Very powerful stuff. It's easy to write code that's particularly hard to read, but it's just, it really makes your life so much easier than having to do this in the raw string functions of a language.
Java has this built in?
Java does not. Perl has excellent regular expression facilities, and they really pioneered this. Fortunately, everybody's copied the Perl stuff. So it's in Tcl now, and somebody has built the Perl regular expression package as a Java library that is available somewhere on the net that you can download, though I don't think it comes from Sun. So there is a regular expression package for Java. And if you ever have to do a lot of string processing, trivial string processing, I highly recommend you do that. Doing it by hand is a unbelievable nightmare. More sophisticated string processing, especially if you're dealing with complex languages like that you need to interpret, is a parser. And a parser is basically a thing that maps from strings to trees. And the details of the string to tree mapping are mediated by a grammar, which is a bunch of rules of the form, X goes to ABC. Not important now, but so you write a bunch of rules, and you give it to a parser, and the parser will give you, if you give it ABC, will give you back a tree that looks like this. Okay, and of course it works recursively, so that if you give it that's a big B, and we have B goes to BD, it will give you a big B node here, and maybe a BD node here, something like this. Writing a parser is an enormous nuisance. There's a lot of theory that goes along with writing a parser. Fortunately, you almost never have to because there are tools to help you do that. But sometimes, if you ever find yourself doing this, having to interpret complex strings, things that don't quite fit regular expressions, examples are anything that looks like a programming language, anything that looks like a natural language, English, Spanish, whatever, probably needs a parser. There are things called parser generators. Some nice tools under Unix are called Yak for yet another compiler, and Lex, which I forget what it stands for. These two tools are great because you can give them a grammar and it will automatically generate a parser for you that will parse that grammar and dump out the trees. Very nice.
What's an example of grammar we would give it?
Probably just the sort of rule that, for example, if you were doing English, you would say that a sentence is a noun phrase followed by a verb phrase, and then a noun phrase is, say, a noun followed by a, it's maybe an adjective followed by a noun followed by a verb phrase, and so on. And then you finally get down to defining a bunch of words of what your nouns are, what your adjectives are. Give that all, and it will come up with something that will parse English, if you can do a really good job at that. The model view controller pattern. This is just very powerful. You have your data. You have multiple views, possibly, that display the data. And then you have a bunch of methods that update the data. And it just really nicely separates the code for this, this, and this. It's just a nice way to think about things. So not too much more to say about that. The last structure that comes up a lot, especially with stream processing, is called pipeline. And here you have a series of stages of processing connected by our old friend, the FIFO queue. Okay? And you have... Okay, so these are, each one of these, I drew them as circles because often they're running as a separate thread. They're taking data from here, off the FIFO queue, doing some processing on it, and pumping it out over here. For example, an MP3 encoder is going to be taking audio out of here and processing it and dumping it out over here in encoded format. Any stream encryption algorithm is going to be taking raw text, encrypting it, dumping encrypted text. And then later on here, you could either be writing to a file or a stream, or have more processing stages. If you look at the early stages of speech recognizers, you have a long chain of these things doing signal processing, where initially you are doing fast Fourier transforms on your data, then you're doing computations on the fast Fourier transforms, then you're doing some matrix rotations, and you have about 5 stages of processing that goes along. And it's nice to have them all working in parallel because data is coming in at real time, okay, and you need to be keeping up. You can't wait till you get all the data and then do all this phase on it, this phase on it, this phase on it. You're kind of operating in the stream. As the data comes in, you're gradually pushing it down this pipe. And these FIFO buffers mediate that nicely. So another place where that's surprisingly useful is network protocols. This is my standard way of doing packet systems when I have to do network protocols. I start with the idea of a FIFO, which is my read queue, and that goes into a process whose sole job is, okay, this is a queue of packets, okay, and this is actually I've got the arrows the wrong way. This is our read queue, so this is a queue of packets, and this is our read process, and his sole job is to take bytes off the network, assemble them into a packet data structure, an abstract packet data structure, and put them on this FIFO queue. Okay, that's all he does. He goes, wait blocks on the network, builds packets. All right, and similarly on the write side, you have a write queue, and then a process whose sole job is to wait for something to show up on the queue and then write it off onto the network. Okay, this is a nice organization because now the rest of this guy doesn't know about the network at all. All he has to think about is the rest of the application just operates in terms of packets. It can read packets off this packet queue. You can have a process, the thread that runs around, reads off the FIFO queue, figures out what it's supposed to do to the packet, does it, and maybe writes something. When anybody wants to do output, they just put a packet on the write queue of this guy. So I spent a little bit of yesterday afternoon and the day before starting to sketch this out and implement this for the Gnutella thing. So the first thing I did was build exactly this, and I usually call these a connection. And sometimes you can optimize this. For example, if you know that writes are not going to block and are always going to be fast, you can kind of make this invisible. You still have something that looks like a method that looks like queue this packet, but what the queue operation actually does is goes ahead and writes it. You kind of splice out that buffer in this thread, okay, and just have the queuing thread write it. As long as the writes are fast, it never knows. Similarly, if the packet processing part is going to be fast, if you know it's going to be fast, you know it's never going to block, and you know that you're not going to get packets so fast that this guy is going to have to be working all the time, you can have him kind of splice this out and go ahead and have this thread go ahead and process the packet before it goes back to try and read the other one. That's an optimization, but from the outside, it's kind of invisible. But this is a nice structure because you can, when you can have the constructor set these things up, make the connection, and then start the read thread, which is them waiting. And then it's just an atomic unit from the outside. You read packets and write packets. And once you have one of these things, it's really easy to then clone them. So every time you want to make an outgoing connection to a new thing, you just call this constructor and make one of these things. Similarly, it makes your server listener loop pretty easy. You just have a thread that listens on your socket. And every time it gets a connection, it just forks off another one of these. All right? And now you have these nice set of uniform things. You can put them in your connection table. All right? And this you can hook up to your connection view. So these guys are essentially your controllers on your connection table. Here's your view on the connection table. And then you can have a ping thread, which just runs through this table periodically and ships pings off on them. That's all cool. So what problems do you have left? You have the problem of how do you do the processing, and then how do you structure the guts of those? I found that a nice structure for those, I have two kind of main objects in there. I made a buffer object, and then I made a packet object, which represents packets, which is really an abstract class and has one real subclass for each of the 4 packet types. I didn't bother with that loser 5th one push. Okay, so what buffer does is it's the thing that actually reads the network. It's essentially this abstract data structure. You can say, read n bytes off the network and give me this abstract buffer object. Or here's an abstract buffer object, write n bytes to the network. All right? And then so that's the connection outward. The connection inward is you have a bunch of access routines that turn the buffer into data types. So I wrote something that, what is it called? Read unsigned int, and then a size, which is either 1, 2, or 4. And what this does is read 1, 2, or 4 bytes out of the buffer and gives me back an int with that value in it. And sometimes you need another one. You need a read bytes. And that's probably close to it. So then, once you have this abstraction, I had another object up here, which was header. Building the header is pretty trivial. You say, you call this buffer and say, give it a socket, say, read me 17 bytes. I think it's 17 bytes. Then you call a bunch of these read uint things, and you've got all the data out of it, so you've built a header. You give the header and the socket to the packet constructor, which says, how many more bytes do I have to read? You go get another buffer that has the payload in it, and then you read out the payload-dependent data using these read uint functions into each one of these things. Now, from the other side, you can have constructors on these guys that say, all right, I want a Pong message that has this data in it, or a query with this data in it, and it makes it into an abstract packet object. And then you have methods that essentially do the reverse of this, that will take integers and write them as 2 byte, 4 byte, whatever, into one of these buff structures. Then you just tell the buff structure to write over the network. And if you organize it that way, it runs pretty smooth and is actually remarkably fast to do. The part that I haven't quite gotten together yet, or almost, you can then use polymorphism on these guys to build your packet processing. You can put on these things a process routine or a reply routine. You've basically got to take the packets, figure out, is this a request that I'm supposed to do something with? If it is, and if it's a request, I need to send a reply and also forward it. Or is it a reply from something I sent out? And if it's a reply, is a reply for me? If not, I forward it. If it is, I look it up in my table. If it's a reply for me, then I just take the data out of it and put it in one of my other tables. So, you've got to have a search result table, and probably this one gives me the willies, the packet match table, where you have to tell, use to tell whether this is your reply or whether you should forward and that sort of thing. Anyway, that was a digression from the pipeline structure, but this whole thing really goes together nicely. And so for any of you who are panicking or looking for inspiration, I would recommend at least thinking about this structure. All right, I think I'm out of gas. There's a couple things, a few sentences in the notes about client-server and 3-tiered architecture, but we've pretty much talked about that, so I won't belabor it. And I'll let you get back to the projects. Good luck.